Hello and welcome to second lecture of client-side application programming. Today we will build upon what we've learned last time, and we will focus on single-page applications mainly, and I will also cover some technical details regarding specific APIs inside the browser. Web applications often follow the three-tier application paradigm. That basically means that the entire application is divided into three separate parts. The presentation part, which in case of web application typically comprise HTML and related stuff like CSS. The data part, which typically comprise data schema in database or database management system. And the middle part, the business logic part, the application part, which actually handles everything else. In case of single-page applications, this business logic part actually shifts from the web server, where it is present in traditional CGI-like applications, towards client side. That leaves mainly the database at the server side. So the web server becomes mostly a clever wrapper around the database and data services, and also handles some remaining stuff like security, which cannot be easily shifted to the client side alone. Although this shift to the client side is beneficial for the user experience, as the whole application behaves more like a desktop application, and all the HTTP requests, meaning all the server interactions, are handled asynchronously and covertly, so the user does not have to see them. It has certain pitfalls for the programmer. First of all, it has to somehow avoid basic functions of the browser, like browsing. The browsing, which is a native function of the browser is in fact named after this feature, has to be discouraged. Meaning, in many cases, we do not want the application to submit normal forms in a traditional way, which actually means reloading the page, or following the hyperlinks, which also initiate browsing. Also, this means that the server architecture is completely different. Normal frameworks for HTML rendering are useless here, so the server remains very thin, and as I said before, it handles only the data storage and some security issues. There are also some disadvantages of this type of application. First disadvantage is application bootstrap. The bootstrap may take quite a long time because we need to transfer all the data to the client side, meaning not only the JavaScript part, but also all the data which are necessary to display the application for the first time. So it can take much longer time to boot the application itself. And also it's harder to program because the browser itself is much less stable execution environment than, for instance, desktop. So we have to modify the application or design the application in a way that is suitable for multiple browsers. Let me start by covering several technical details. First of all, we have to notice that every browser can open multiple windows, and every window may have multiple tabs. I've just checked. Currently, I'm running over 20 tabs in 4 different windows. So it's a kind of normal thing that people tend to open multiple pages at once. Meaning all of these pages can basically hold a web application. However, only one or very few of these applications are simultaneously visible to the user. For instance, if you have a window, only one tab in this window can be selected, so only one application can be directly visible to the user. Actually, this is particularly important for highly interactive applications like computer games, but it might be interesting also for other applications. Fortunately, we have a simple API which can be used to detect whether the application, whether the document being displayed in the window is actually visible to the user, and we can modify our application to act accordingly. For instance, if the game becomes hidden, we can pause the game so the user won't lose any advances in the game or can be attacked in the game. Speaking of visibility, there is also a problem with scrolling control. So sometimes if the page is too long, it does not fit the viewport of the tab or of the window. So we need also to handle scrolling. This becomes particularly important when you're programming single page applications, because when you're modifying the application every time the user performs an action, sometimes you might want to control the scrolling as well. Fortunately, this is very simple. We can use scroll to and scroll by to use coordinate system to scroll to the particular coordinates, or we can scroll into view a particular element. So if you want to make sure that particular element that's being currently modified or active has to be visible, so we can scroll it into a view. The thing that is pretty important is the location object. Since we need to handle all the stuff at the client side now, we need also the information regarding the current URL being displayed in the address bar. The location object can be accessed by two APIs. It's present as a property both in window and document, and it's basically a parsed URL, so it holds all the separate parts, separate substrings of the URL, which might be important for your application. We can also modify the location object via methods. These three methods, actually these two methods, assign and replace, can modify the location object by assigning a new URL to this object. Assign just push the URL into the history. Replace replaces the current URL in the history, and reload does not modify the history, just reloads the current URL. All these three methods actually initiates browsing. So in normal situations, in single page applications, these three methods are actually those which we are trying to avoid. However, there are still situations when we need them, because we need to initiate browsing for other reasons. Also, some important things, important methods and properties are in the window object. First of all, we can use window open to open another window or another tab, depending on the settings of the browser, which will hold a new URL. That might be sometimes very useful if you want to create pop-up windows, or you need to create a new window. For instance, if you're displaying a help page for your application and you don't want to lose the application state, so you might want to open it in another window. I would point out a very important technique here. Sometimes, since changing the URL causes browsing, we can change only a small part of the URL which does not do that. This part is of course hash, or the fragment part of the URL. So if this part is changed, the browsing is not initiated. Therefore, we can sometimes use it to stash at least some information into the fragment part of the URL. And if the state of our application changes, we can just change the hash part of the URL without actually initiating browsing. And internally, then we can use this particular event handler to detect if locally the has been modified in the URL, and we can act upon this. Also, unloading of the page might be important, because if we cannot prevent browsing, or we need to do browsing for other reasons, these two events become very important. This one will trigger just before the page is being unloaded, and then this one after the page is being unloaded. So this is very important, because if we want to finalize some operations, if we want to quickly stash some data, for instance, so we won't lose all our state, this is the code, this is the event handlers we should use for that. The last thing I would like to present in this technical introduction is the concept of history. The history is basically a history of browsing, so it inherits the original concept of the browsing. So when the user moves to another page, the browser captures the previous page, pushes the previous page into history, so the user can go back and can return to the pages he or she already visited. However, this concept is not entirely suitable for modern applications, because, as I said before, we are trying to avoid this browsing concept altogether. But we can do a slightly different thing. We can use a history API to push our application state. So we can track our application state in the browser history, which will actually simulate the same thing as moving to another page, but without the unfortunate effect of browsing, thus reloading the page, thus losing all our memory. The API is accessible via the history object, and it has several important things like back and forward, which triggers the same operation as back and forward button. However, the most important part is this push state. We can actually push our arbitrary, our custom state into the history. The data here is a normal JavaScript object. Title is the new title of the page, and notice that we can push a new URL along with the data, so we can actually replace the URL being displayed in the address bar, but without actually initiating the browsing effect, without erasing our memory. So this is the way how we should handle changes of URL, because URL still might be important. We need to keep the URL in sync with what's going on the page. So this is what we can do to manage our state programmatically whilst giving the appearance of actually doing simulated browsing. If the state is actually changed later, for instance, if we have pushed the state and somebody pushes the back button, on-pop state event will be triggered, so we can also handle this event and be ready to handle back and forward movements, but on the push state. This API allows us to do very elaborate things. Besides the thing that we can simulate the browsing, we can also use the push the state and later back and forward buttons to simulate things like undo and redo operations in an editor, for instance. This brings us to a slightly different meaning of the URL in case of single page applications. First of all, we have to point out that the URL is no longer relevant for the server side. Actually, this is not 100% true. Sometimes the URL can still be relevant for the server side. For instance, if we performing server side rendering, but I will get to this special case later. The URL is basically, all the URLs of the applications are basically pointing to a single file or a single set of files, single initial file at the server side, which is basically the Bootstrap HTML document. The routing is performed at the client side and has slightly different meaning than what we are used to at server side. First of all, the routing is performed only when the JavaScript bootstraps, so only once or perhaps after reload of the page. So it's not a common thing to perform routing. It's only part of the initialization of the application. Second thing, it only identifies the views or top-level components. Routing or the URL never identifies an action. Actions are handled separately immediately by JavaScript, and they are not manifested themselves in URL in any way. Actually, I'm talking about the URL of the application. Of course, the REST API that handles actions at the server side also needs URLs, but this is a different set of URLs. Now I'm talking solely about the URLs that represent the client side, the application itself. So, as I said before, the traditional browsing should be prevented, should be discouraged. So we just replace the traditional browsing with component swapping, and we can push the state as I just demonstrated on the previous slide. Remember, the URL always identifies only the top-level component or the page component of your application. So a good thing to do is to keep your top-level component currently being displayed to match the URL which is currently being displayed. That means only when the top-level component is changed, you need to push a new state in the history and you need to replace the URL in the address bar. So that covered the most important technical things about the single page applications, and now I would like to move towards the perhaps most important part, and that's the application state maintenance. This is a bit of a revision because I've already presented all the approaches to application state last time, so let me revise these three approaches. First of all, we can embed the state in DOM, or we can use the model view model approach, or we can use the one-way rendering approach. The first one, the embedding state, is actually not suitable for larger projects, thus it's very unsuitable for single-page applications. Therefore, we will focus on the later two approaches. Just remember, just for revision, this one is being used in the Angular framework, which is one of the first framework founded for the single-page applications. This approach is used in the React framework, which is currently perhaps the most popular framework for single-page applications. The model view model design pattern is actually a specialization of model view controller design pattern, and it aims at simplifying the relationship between the view and the model. It works as follows. It actually interrupts this connection between view and model by adding a view model in between. And this view model acts as an intermediary between these two parts by presenting the data in a slightly different format, which is directly used by the view. So basically, view and model are just like brothers with different representation of the data, and the view and view model here are connected via bidirectional data binding. So the main point of this framework is that this part can be done semi-automatically, preferably using some declaration. So we just declare the bindings, and the rest, the communication between these two parts, is handled solely by the view model framework implementation. Although the model view model has many benefits, it has also some setbacks, some pitfalls. Particularly, it can be quite troublesome in very complex scenarios. Normally, in simple scenarios, it's pretty straightforward. We have this action probably triggered by the user, and this action is being processed by controller, and controller reacts upon this action by modifying the model, or the view model in this case. And since the model and view are interconnected by bidirectional links, the view is immediately automatically updated, so the user immediately sees the change in the data, the change in the application state. The trouble comes when we have multiple components on the same page, and each of these components have their own models, view models, and their own views. So all these components has these bidirectional bindings, but also some of these components are interacting between each other. Therefore, modifying one model may lead to a cascade effect, which actually modifies a different view, and this modification is propagated back to this view model, which can be propagated to this view, etc., etc. The most important part, the most problematic part, is that we need to check out whether there are loops in these dependencies, because if there are loops, the modification can actually trigger an infinite loop of changes. So we need to check out whether there is a loop in this schema. So I give you a brief moment to check out whether there is a loop. Yeah, you can pause the video if you would like. Okay, if you checked it, there is actually a loop. So this model leads here, so we can to this view, this leads here, here, and back here. So there is actually a loop in this view model set of schemas. Therefore, if we take an inappropriate action, some action that modifies some data which are actually shared amongst these models, it can cause a repetitive loop of updates. One of the first attempts how to deal with this problematic or potentially problematic looping updates was presented by Flux framework. This framework slightly modifies the model view model pattern. Actually, it breaks it down to simple pattern to avoid this kind of loops. In this case, if action arises, if some event triggers an action, the action is processed by a dispatcher, which actually processes always one action at a time. And the results can be propagated to store. This is just a different name for the model, basically. And the store then triggers a rendering function that projects all the changes in the store into the current view. Since all these arrows are in one direction, there is no way how it can loop infinitely. So this is a basically one-way rendering paradigm. If the view wants to trigger an update, it must create a new action, which then subsequently will be processed by dispatcher. Of course, this does not prevent the looping altogether, because in theory one action can be processed by dispatcher, produce some update which will trigger the update of the view, which will inevitably create the same action. So in theory we can still be looping here, but the scenario when this would happen is much more unlikely. Today, most developers prefer another framework which is called Redux, and it is an informal successor of Flux. It comes with the same paradigm, so it uses the same principle. However, it makes some modifications which make it slightly better in certain situations. First modification is that there is only one store for all the views. So all the components, the whole page, actually the whole application shares a one store, and the state is basically one object. Second thing, that there is no dispatcher as there was in Flux, but instead the action or the actions are processed by reductors. And reductor is a pure function which takes the original state, the action object itself, and produces a new state. So it means that the state is never modified directly, but instead a new state is created every time an action is processed. This is actually very helpful because the programmers are sure that whenever they touch the state is always consistent. It does not happen that only part of the state would be modified, because always when the state is replaced in the store, it's replaced with another consistent state object. Here we have a detailed schema which would explain the processing of an action more closely. So first of all, remember that the state is actually immutable object. Second thing we need to know is what is action. Actually, action is also a simple object. There are certain limitations. For instance, this object must be serializable, meaning it must contain only literals or nested objects and arrays without loop references. And finally, the reducer, which takes these two things and put them together, is a pure function. It means that this function has no internal state, and it computes its outputs only based on the input action object and the previous state. No other data can be used in this reducer. And finally, the new state is the modified state object. Here we can use clever techniques like immutable JS library so that we don't have to copy the whole state to the new state, or in some cases we can use shallow copying. Since the original state is immutable, we can replace only those parts which actually change in the new state. So there are ways how to make the copy, let's say, clever with a very low memory footprint if only a small part of the state is changed. This approach has many benefits. One of them is also the thing that the debugging is much more easier, because since actions are serializable, we can record all the actions, we can serialize them in a log, for instance, and since each state is immutable object, we can also keep the states in a log, we can also save the states. This also helps implementing things like undo operations, because if we want to implement undo, the only thing we need to do is to save the older states from the store, and if undo operation is performed, we just go back to the previous state which is saved somewhere else. Let's take a look on a small example how Redux actually works. Let's start from the bottom actually. Here we have the initialization of the store. This is the initial state object. You can see that this state is very simple. It only holds two counters which are normal numbers. The store is created using this function. This is a function of the Redux framework, and the function holds the reducer, which is the main pure function used for reducing states, and the initial state object, which is the first state of the store. Later we can use dispatch function to dispatch actions. As I said before, an action is a simple object, so this is the object, immediately constructed object of the action which will be dispatched. The hard part, the more tricky part, is in the reducer, so this is the function which is used to take the old state, take the action and produce a new state. In this case we have to come up with our own way how to recognize actions. So in this simple scenario I have decided that all actions should have property type, and this property will be kind of an enum, kind of an identifier of the action, so the reducer will depend on the type of the action to process the action. In this case our action is very simple. We are using inc action, which is this constant to recognize the type of the action, and the data of the action holds the counter, which is a reference to one of these two counters. So it aims at the counter which should be incremented by this action. And the reducer performs a very simple thing. Yeah, forgive the switch over here. I just wanted to keep this code very simple. Normally there are much better ways how to write this code than with switch case construct, but for the time it should do. And this construct will recognize the type of the action, so it will recognize that this is the increment action, and create a shallow copy of the state, because we are modifying only one counter in the state, so we can afford to shallow copy the rest of the state, because we know that states are immutable. And we will replace the counter in question. These brackets mean that the counter variable is dereferenced as a string, which is used as the property name, and we will increment it, so we will use the old value plus 1 to create the new value in the new state. Having immutable state has certain advantages and disadvantages. As I mentioned before, having immutable state is beneficial for consistency, so we always know that the state is consistent, and also it simplifies snapshotting, like undo redo operations, or snapshotting for the purposes of debugging. It also simplifies the change detection, so we can easily detect which parts of the states have changed, which is very beneficial when we are connecting Redux and React. So for the visualization purposes, we can easily detect which parts of the state have changes, so which components should be re-rendered. On the other hand, this copying raises some issues, some questions regarding efficiency and memory footprint. So in order to do this efficiently, we have to implement the state wisely using shallow copies and shared references. For instance, first a good idea is to decompose the state to smaller states which are represented as objects. This decomposition may be hierarchical, so all these blue rectangles are in fact objects which are somehow embedded in the state. If something changes, for instance, if we perform modification in this particular object, the only thing that needs to change are the object itself and of course all the parent objects. However, all the blue objects still remain the same. They are normally passed down by reference. They don't have to be cloned. There is one other benefit I haven't mentioned so far regarding the state decomposition. If we decompose the state in this way, we can also do the same with the reducers. So if we have separated objects, individual objects of the state, we can have individual reducers that process only these objects, and then there are tools which allows us to easily combine these reducer functions into one final main reducer function. As I mentioned before, React and Redux are often used hand-to-hand. There is a tool called React Redux Connector, and its job is to connect the state in the Redux store and the components on the page. In fact, the job of this connector is twofold. First part of the job is that it provides data from the state, only the focus part of the data of the state, to the components in the React, and also it provides clever wrappers for the dispatching of actions, so the actions can be dispatched simply by calling functions. Therefore, these functions can be later attached as event handlers, and thus event handlers will trigger easily a dispatching of actions. The most important part of this connection is actually formed by the group of selectors. Selectors are functions which are responsible for selecting the right part of the state from the store and attach it to components. These selectors are actually essential for the performance of the whole application, because if you choose them, if you write them in a wrong way, you can easily end up re-rendering the whole page every time a small portion of the state changes. So it's very important to focus these selectors so that only the really needed part of the state is attached to every component. On this note, it's also very good idea to decompose your Redux store state in the same manner you are decomposing your components in the React. So if you kind of make these two things compatible, then you can write selectors very easily. Perhaps the most important thing we need to observe when writing selectors is that the results, actually the changes in the results, are monitored using the equality operator. That means that when something changes in the selector outputs from the previous call, then it's indication that the component should be re-rendered. Actually, the situation is slightly more complex than this, but this just gives us a good idea how it works. So in case we have a straightforward selector like this one, which just selects one sub-object, probably an array by the name of it, from the whole state, this selector should perform good in case that the state modifications hold up to some outline recommendations I have mentioned before, like the shallow copying and modifying only the parts that actually needs to be modified. However, sometimes the selector may perform other features like filtering the data or transforming the data. Let's take a look on this selector. This is a very similar one, but the items are subsequently filtered and they are mapped to a different format, so they are transformed into a different format. Although this can be done in the selectors, there is no rule that would prevent us doing this in the selector, it will actually ruin the testing over here, because the map function will always create a new array. So if this new array is compared by the previous array using the equality operator, it will always turn up to be a new array. Although it might contain the same items, but it won't be detected because only the equality operator is used for the performance reasons. Therefore, we need to use a smarter approach how to deal with these newly created objects and arrays inside selectors. One of the approaches we can take is called memoization. Actually, don't get confused with memorization. This is a different term. This is not a typo. Memoization is a caching technique which allows us to cache inputs and outputs of pure functions, and in case this function is repeatedly called with the same inputs, we just reply with the output from the cache instead of computing them again and again. Typically this works as a transparent wrapper, so we have this memoize function, and this is a function which wraps another function. So we have this pure function like selector, and it's getting memoized. So we have a new function which actually first takes a look into the cache and tries to serve the request for computation from the cache, and if there are no sufficient data in the cache, it will actually call the initial function, save the inputs and outputs in cache, and yield the results as a normal function. So basically this memoized function works the same way in most situations as the original function. If it's a pure function, it works exactly the same, but it does not have to call the internal function all the time. In case of selectors, we can do with cache of size 1, because we actually want to cache only the last result, because if the inputs change, then we expect the outputs will change as well. So we need to recompute them normally, and we need to produce a different result to indicate that the inputs were changed as well. This is actually not a technique bound to JavaScript and bound to React Redux. The same technique can be used in some other frameworks, in some other situations. Most often it can be used to reduce time of computations at the cost of having the data cached. So if you have a small inputs and small outputs and very long time to compute them, then you can use this technique to optimize other things as well. Of course, in these cases, probably with cache of a size larger than 1. However, in JavaScript, this special technique is very useful when we are trying to detect changes of objects using equality operator, like in the case of selectors in a React Redux connector. I would like to conclude this little introduction to Redux with a short talk about asynchronous actions. Normally, all Redux actions are processed synchronously, so the reducer is invoked immediately as the action is dispatched. However, in some scenarios, this behavior is not ideal, because in JavaScript we often deal with asynchronous operations. For instance, if we are fetching data from the REST API. So we need to modify these operations so they can be correctly handled in Redux. For instance, we can split them into multiple Redux actions. First action typically represents when the asynchronous operation starts. So the data inside the store has to be ready for the fact that that there is some transition when the data are being filled. So normally when we have like data from REST API, we have also some state attached to this data, and this state must allow for the pending state, which means that the data are currently being loaded, that the asynchronous operation is currently running. Then we need an action which is triggered when the operation is resolved. Typically the pending state will be removed and the final data will be filled into the store. And also we need a special operation, a special action that handles failure operations. So if the pending permission is rejected, we need to remove the pending state, and possibly if we are doing some optimistic updates, so meaning we're doing some premature updates in the store which haven't been saved to the server yet, we also need to revert these optimistic updates if failure occurred. Actually, this is kind of tricky to implement and hard to maintain, so there are frameworks and libraries for this. For instance, there is the Redux Thunk library, which implements all this stuff as a middleware for Redux, or there is a Redux Saga library, which can also help you with maintaining these asynchronous operations. At the beginning of this lecture, I have mentioned several drawbacks of single-page applications. Now I would like to get back to one of them, and that's lengthy bootstrap. Although single-page applications can improve user experience by actually reducing amount of data transferred between the server and the client, or at least hide these transfers to the background so the user is not bothered by the traditional browsing, the bootstrap of these applications can be much more complicated in the terms of time demands than the bootstrap of a traditional CGI application, since actually there's typically no apparent bootstrap of a normal CGI application. So how it works normally, when the application is bootstrapping, there is some static contents which typically comprise some initial HTML, most importantly the JavaScript bundle that holds all the libraries, all the implementations of the business logic at client side, basically everything your application needs, and possibly some cascading style sheets. Although this data might be cached, so they don't have to be reloaded every time, the initial data for the application, which are subsequently loaded from the API, cannot be cached. So once the application is booted inside the browser, once the JavaScript is running, it will perform many requests to the REST API to get all the necessary current data which should be displayed to the user. So this operation is kind of a less efficient because we are downloading the static content and then we need to download all the dynamic content, which is kind of unavoidable, and normally both these parts are downloaded from the same server. To optimize this API calls right after bootstrap, we can perform a technique which is called server-side rendering. Yeah, if you are confused right now by the shifting between the server side and client side, this confusion is rational. So before in CGI applications we were rendering the HTML at server side. Now I'm telling you that the single page applications do this at client side, and now I'm telling you that there is an optimization which go back to the server side and again renders the page at the server side. Yeah, I realize that this ping pong between the sides can be slightly confusing. However, I will explain in more detail where this should help. So the thing is, don't need to perform all the API calls via a network, but we can perform them before the bootstrap or right after the bootstrap, but at the server side. So we avoid some unnecessary server traffic, the communication between the client side and the API. In order to do this, we need some frameworks like React and Redux, for instance. But remember, in Redux, the store holds an immutable state which can be serialized. So we can perform all these requests at the server side, prepare the state for the Redux, and then serialize only the state and transfer only the state to avoid repetitive API calls. Of course, there are some limitations. One of these limitations is that the server has to run JavaScript, of course, unless you want to re-implement all the reducers in two languages, which would be very tedious and let's say very error prone. So it's a good idea to have only one set of reducers. On the other hand, remember that the reducers are pure functions, so they do not need any special environment. They just run in JavaScript and they just get two simple objects as input and produce another object as output. So basically these functions may run as well on client as well as on server. Also, sometimes we can use this technique to pre-render the initial HTML as well. For instance, the React framework allows HTML serialization, so you can take the virtual DOM and instead of displaying it, which would be impossible in Node.js at server side, we can serialize it into normal HTML. So this will produce the initial HTML of the page, and this step will produce the initial serialization of the Redux store, and these two things can be easily transferred to the client side and deserialized. So the whole application can bootstrap not from scratch, but it can bootstrap from some initial predefined Redux state and from some pre-rendered HTML, which would be rendered the same at the client side if there weren't for this optimization. I will explain this one more time on the diagram, which might be more understandable. So now when an application is want to bootstrap, when the first initial request is passed from the client, the answer is not given immediately, but first the web server runs the bootstrap script for given URL at server side in Node.js. Remember, I told you before that the URL is no longer important for the web server part. So if you're employing this particular optimization, it is actually important for the server part because the server needs to perform the routing at the server side right now. Then the server performs all the API calls which would be normally performed by the client, but assuming that these two things run on the same hardware, on the same server, this is much more efficient than running them over the network. And finally, the initial HTML document is passed by with the pre-rendered HTML and initial Redux state, which is typically serialized in something like JSON. And of course, we still need the other static content like the Bootstrap script itself, CSS, etc. This does not remove the necessity of communicating with the API, but these calls are typically performed later after the user performs some modifications, some actions. So we don't have to encumber the API right away after the boot script of the application. In the last part of this lecture, I would like to focus on several issues that are directly related to state maintenance. First technical issue is the fact that your application may be opened in multiple tabs or multiple windows. Actually, that's a normal behavior for the users, and there is very little you can do to prevent this, so you better get ready for this possibility. In this case, you have to distinguish several types or several categories of application state. First one is session specific, which means, or window specific, which means that this state should be isolated from all other states, even though they are sharing the same application. The typical example would be when the user performs something like eShop order. So there is kind of a wizard that takes him through individual steps of this order, and the state of this wizard is a local state, is a session specific state, which should be separately stored in each window. If you save this state in a local JavaScript variables in normal JavaScript memory, there is no problem here, because actually all these contexts are separated one from another. So this would be like a normal way how to implement things. Actually, the more complicated situation rises when you want to have an application-wide state, so some state which is shared among all the instances of your application, amongst all the windows. And a good example would be something like eShop item stock availability. So when the order in one window is conducted, the stock availability should be reduced so the user wouldn't accidentally create the same order for the last item in multiple windows simultaneously. The thing is that this state has to be synchronized amongst the windows, and that's slightly more complicated. I will explain this in short order, what APIs we have for that. And also remember that there is also persisted state. Of course, persisted state is always application wide, because if we are persisting something at the server side, this data are shared amongst all the windows. However, remember, the data are typically cached at the client. Normal way how to do this would be to cache the data inside JavaScript memory, meaning isolated for every window, meaning it's the session specific state, but the data are actually application wide. So if you have some sort of cache, it might be also advisable to somehow move this cache into the application-wide state and perform some synchronization on this data. However, not always. Sometimes some parts of this data might fall into the session specific. So this is tricky actually. You have to decide whether the persisted state or the cache data from the server has to be stored in application-wide or in session specific part of your state. Also, there are some tricky questions, like, for instance, where should we store authentication tokens? So if your user is logged in, if you have issued some authentication token or other session, let's say a session specific token that maintains the connection with the user, the question is where you should store this token. One way to go is to store it in a session specific state, because I've already used the word session in this context, so perhaps this should invoke that the token should go to the session specific state. On the other hand, if you have an application and this application allows opening new tabs or new windows immediately from the application itself, for instance, because it still uses normal hyperlinks, then it might be better idea to save the token in some place which would be actually application wide. So in all the tabs, all the windows, the same user will be logged in, and the user won't have to log in separately in every window. Yeah, it's a tricky question actually. Both approaches are correct. It depends on what your application should do, how your application is designed. In my case, I typically fall to the way to store the security token or any other logged in user related stuff in an application wide manner. I find it slightly more convenient than using separate token for every session, for every window. However, there are situations where the session specific state would be advisable for the security tokens as well. So it's not a clear issue. I promise to present some techniques how to allow communication between multiple windows or multiple tabs. First of them is the cross-document messaging. This is a relatively safe way how to send messages from one open window or tab to another. Actually, there are some limits. One of the limits is that you have to get a pointer to the other window. So normally this is used only in specific situations, like when one window opens another window. So the original window holds the target object of the newly created window. The way is the API is actually very simple. The window object has this message event, which is triggered every time somebody sends message to this window. So if you have a target window object, you can send the message via this function, and this event will be triggered on the target window. The message, of course, has to be something which is serializable and can be easily transferred. You cannot transfer API objects, for instance, and also there are some limitations regarding the origin. So sometimes you can use it to prevent cross-origin, cross-site data transfers, which are typically undesirable. Let me give you a quick example how this works. So first of all, we have this code in a main window. This is the original window which will initiate the opening of another window. So we call window open with some technical details like URL, and this will create a pop-up window or a new tab, and the target window object of this window will be saved in this variable. So later we can use it to post messages to this newly formed window. We can also receive messages. Of course, the communication can be bi-directional, but it has to be initiated from the original window because only the original window has the target window object. The pop-up window, the newly formed window, has to create this event handler, which should be attached to the message event. And as you can see, it can process the data from the event, and this event object also holds a variable source, which actually points back to the original window. So this is the way how the newly formed window will get the target window, the initiating Windows object, so it can post messages also back. The second API I wanted to present here is the web storage API. Actually, this one will help you to kill two birds with but one stone, because it's actually persistent storage for keeping persistent data, and it also allows you to share the data amongst multiple windows, so you can use it in both ways. It's somewhat similar to cookies, so it also stores key value strings. However, these strings are intended for the client side only, so unlike cookies, it won't be sent to the server side. Nevertheless, cookies are still a valid option for some situations if you need to share your data also with the server side. Normally you don't want to do this, except for the cases you are using something special. For instance, if you're using the server side rendering I mentioned before, it might be a good idea to include the data into the cookies, so the server will see the data as well when performing the initial bootstrap rendering. There are two storages. One is named local storage and the second one is named session storage. As the name suggests, the session storage is session specific, so it's per window, and also it's deleted when the window closes. However, the session storage will allow you to persist session specific data if the page should be reloaded, for instance. Local storage is per website, so it's shared among all the open windows which display the same site, the same web application, and also it's persistent in the terms it will survive closing of a window. Actually, local storage and cookies employ the similar pattern in persistency, so they are persistent theoretically forever. However, the user might want to initiate some purge in these types of storage. The user might want to initiate purging the cookies or purging the local storage, so this data can be removed if the user asks for it. Also, there are some strict quotas, so both these storages cannot be used indefinitely, but you have to limit yourselves. Most browsers currently employ about 5 megabytes per site quotas, so you can't save anything in this storage, but 5 megabytes should be enough to store normal intermediate state, for instance to save the Redux state if need be. The quotas can be configured in a limited way. Technically, you can override this 5 megabyte limit. However, to do so, you need to dig deep into the configuration of the browser, so it's not something a normal user would normally do. The API for both local and session storage is the same, and it's very simple. The API object is provided via these variables in the main context, and as I said, it's very straightforward. We can use get item set item to modify the values. Actually, this is very similar to map API. Then we can iterate the data, and also we can remove individual keys or clear the whole storage. Also, there is this window storage event, which is used to notify other windows when the storage changes. This goes only for the local storage, of course, because it makes no sense to monitor session storage. So if the storage is modified by one window, the other windows got this event, and the event object will hold all the necessary information about the change, namely which key was changed, the old and the new value of the key. So each of these windows can keep up to date with the data. So that concludes today's lecture. Thank you for your attention, and as always, if there are any questions, feel free to send me them by email, or you can post comments beneath this video on YouTube.